So now I want to explain how we come up with this and give you a formula for it. Measure, trace on A. Measure A in, well, it doesn't matter which basis you measure A in, but let's say canonical basis. And you get what you get when you measure A in the canonical basis is you get a probability distribution on pure states. So here, I suppose I should have said we're assuming this is, you start with a pure state. When you measure A in the canonical basis, you get a probability distribution on pure states. And this probability distribution corresponds to a density matrix, which is exactly taking the trace of the first qubit. So we can write psi sub AB as equal to summation alpha I E sub I. This is the ith. This is the ith basis element, W sub I. And this is whatever we get when we write psi AB like this. Yeah?
So when you get these measurements, you get a probability distribution on pure states, and this corresponds to a diagonal density matrix, right?
No. Maybe I should do a better example. Okay, let's make up an example. Let's say 1 over root 3, 0, 0, plus 0, 1, plus 1, 1. Okay. Measure first qubit. The measurement outcome, well, we get 0 with probability 2/3. And the residual state, if we get 0, is just 1 over root 2, 0 plus 1. And measure, we get an outcome of 1 with a probability of 1/3, and the state is just 1 in that case. So the density matrix is 2/3 times 1 over root 2, 0 plus 1, 0 plus 1, plus 1/3, 1, 1, which equals 2/3, 1, 1, 1, 1, except I better put a 1/2 here. Plus 1/3, 0, 0, 1, 0, 1 is equal to, let's see. So that's 1/3, 1, 1, 2/3. No, 1/3, yeah, 1/3, 1/3, 2/3. Okay. Now, the density matrix of that thing is 1/3, 1, 1, 0, 1, 1, 1, 0, 1, 0, 0, 0, 0, 1, 1, 0, 1. And we're tracing out the first qubit, which means we need to add this plus this, trace A, you get 1, 1, 1, 2. Because what you're doing is you're just adding this matrix and this matrix. And let's put a 1/3 in for normalization. So this is equal to that. Yeah?
So when you say you're getting a probability distribution on pure states, you mean pure states of A?
Well, if you trace out A, you're getting pure states of B. But yeah. If you measure A, you get a probability distribution on pure states of B. Because here we measured the first qubit, and if we measured the first qubit as 0, we got this on B. And if we measured the first qubit as 1, we got this on B.
But the top one is not a pure state of B.
No, it's of AB, a pure state of AB. So you have a pure state of a joint system. You measure one of the systems, and this gives you a probability distribution on the states of the other system.
Okay.
And these pure states turn into a density matrix in the way we make density matrices out of probabilistic ensembles of pure states. But they also correspond to this partial trace operation. And here, I'm not going to trace B would be equal to trace of this guy, that's 2. Trace of that guy, that's 1, 1, 1, with a 1/3 in front of it. And if you look at that, that state, if you interchange 1 and 0 and the 2 qubits, you get the same thing. So this is, so if you start with this and interchange the 2 qubits, you get this. So that would give you exactly the same calculation for this with 0 and 1 changed. So this is what happens. So size of A is equal to, you can always write a system of a state of 2 systems as a probability, as a superposition on EI, the canonical basis in the one, times some vector in the other. And, that's because that is equal to 1 over root 3, 0, 0 plus 1 over, I guess, root 2 over 3, 0 over root 2, plus 1 over root 3, 1 times 1. So 0 and 1 are these E sub I, and this are the W sub I, and the probabilities are these things squared. And those are the alpha I. So trace A on psi AB is equal to some alpha I squared WI. And WI is equal to, well, the, I guess, partial inner product of E sub I on A with psi AB. Oh wait, no, I want to say alpha IWI is this inner product because it's not normalized. So rho is going to be equal to summation alpha I squared WI WI. I want to say this is summation over I E sub I bra E sub I ket psi bra psi ket E sub I.